So in this video series, we're going to build a device to measure the frequency response of an audio system. And by an audio system, I mean the speaker, the microphone, and everything in between. And this device is useful because we can tell how through this system, audio is either attenuated, delayed, there's reverberation. We'll be able to characterize that with this device. And in this video series, we're going to build this device in 4 parts. First, we're going to create the generator for the sine wave, and then we'll create the speaker interface. And after that, the microphone interface to receive the sound generated from the sine wave generator through the speaker. And finally, we'll build the sine wave receiver to be able to determine what effect the audio system had on our sine wave. So let's get started with building the sine wave generator. So our final system is going to be composed of both our device, where that sine wave generator is going to be, and the audio system that we're trying to measure. Now, no matter why we want to measure the system, the procedure is going to be the same. Maybe we want to see if our room is adding echo, or we want to see if the speakers are not transmitting high frequencies with the same amplitude as low frequencies, or our microphone isn't accurately measuring those frequencies. Our device will do the same thing. It's going to have an internal algorithm that will have virtual knobs that can either change the volume of the sine wave or the frequency of the sine wave. And with that, the device will then measure what the response is. So let's look at the brain of the device to see how it will operate. The goal of the sine wave generator is to generate a waveform, specifically a sine wave. And if we recall from high school math, this can be implemented using the sine function. Now, to do this in GNU Radio, we have to use GNU Radio blocks, because for GNU Radio, one of the ways of doing simple design is to use already implemented functionality in the form of blocks, which we then just wire together. And GNU Radio has a block for this, and it's called the signal source block. Now, one of the things that we want to be able to do, besides just create the sine wave, is we want virtual knobs to be able to adjust both the volume, the amplitude, and the frequency of the sine wave. And we can do that with GNU Radio using additional blocks. So we can use a range block to be able to adjust the amplitude, and then also another range block to be able to adjust the frequency. Now that we've discussed the design, how are we going to build it? Of course, before we can implement the design in GNU Radio, we need to actually have GNU Radio running. And there's multiple ways to set up GNU Radio, either in Windows or Linux, but I found the easiest is to download a GNU Radio virtual machine. And that's what I'm going to show for the example when building this. So what I did was I went to this website, downloaded the virtual machine, followed the instructions on how to set up the virtual machine, and that's what I'm going to then show you. We're going to start from the virtual machine at the command line, logging in and then running GNU Radio. We're now going to create the sine wave generator using GNU Radio Companion. And there are 2 ways to launch it. You can either click on this icon here to launch it, or you can launch it from the terminal. And to show that, you would just type in GNU Radio dash and then Companion, hit enter, and it's going to bring up a blank flow graph. And on the flow graph, there's a description here, and then it gives you a variable which has the sample rate. So we'll first edit the description, and you just right-click, select Properties, And I like to have the ID name the same as the title. And that's just because it's easier for me to remember that. So I'll select that, and I'll make that also the title. And I use underscores as opposed to dashes because that way when GNU Radio generates the Python code from this, it can use that as the file name. Now, the variable sample rate, I like to always just call it FS. So you can leave it as sample rate. And then we'll use an audio standard of 44,100 samples per second. And so this is just a variable that's a Python variable. And then we can save this flow graph. It's always good to save things as often as possible. So, and I'm just going to use this name and I'll put it in the temp directory here. Select save. And what we're going to now do is we're going to add that signal source of the sine wave. And so what we can do is to find it, it's actually called signal source. You can click on the search, the find icon, and start typing in the name, and then GNU Radio will show you all the blocks with that name. And we see here under waveform generators or signal source. If you're wanting to navigate to it, you can simply go through here and then look down at waveform generators, and you can see all the different waveform generators that you have. And one of them is signal source, which is right here. We just drag this block over and then we start to edit it. Now there's a few things we're going to want to edit on this. The first is we're going to need to change the sample rate to match our variable. And also, we're not going to be transmitting complex waveforms with imaginary and real. We're just going to deal with real, so we'll change that to float. And then the waveform, we'll change that to a sine wave. Now, the frequency we want to change with the virtual knob. So we're going to create another variable, and we're going to call it frequency. And we're going to do the same thing with the amplitude of just calling another variable amplitude. Now we can then select OK. And you see that there's a couple of points that are red. That means there's errors, that this isn't complete. So, for example, the frequency is red and the amplitude is red because there are no variables for frequency and amplitude. It's just FS. So if we wanted to, for this variable block, we could look and it's under core and then variables, and we can just drag this here, and we can simply, for that ID name, we're going to use the word frequency and then leave it there, and it changes it. But there's a problem, and that's that we're not going to have any control. We would have to actually change the value each time. So instead, to be able to have more of it, to actually have a knob that we can change, we're going to use what's known as a range option. And this range option you could find by going under GUI widgets and Qt, which is the type of graphical API. And then we could select the range option from there too. And we're actually going to need two of them. So we get rid of the frequency variable because we want to be able to have more flexibility. So instead, we're going to have this variable that we can manipulate in real time. And I also call it frequency. And I like to put the units here. This label is what's going to show up on the graphical interface. And then for the values, I'm going to start it at 3000 just as a default value. That's going to be 3000 hertz, 3 kilohertz. And we'll allow, we can go between either 0 hertz or FS, FS over 2, which would be in the 20 kilohertz range, which you may or may not be able to hear. And then the step size, I'm going to choose 100 hertz. Now, when we do this, you see that the frequency here has changed to the 3 kilohertz, which is the default value because we've linked those variables. And now we're going to link the same for the amplitude, which is in red because it's looking for an amplitude variable. So we're going to call this amplitude and then paste that here. And for the amplitude, I'm going to have it at a quarter of the maximum, where the maximum goes up to 1, and then our step size, just have that as 0.1 for the step size between 0 and 1. And we can see that this now disappears. And so the signal block is still red, and that's because it wants the output to be hooked to something. So what are we going to hook to? Well, we're going to want to be able to visualize this. And we're going to be able to, we want to use a few different blocks for visualization. And we can go to what's called instrumentation. And that's like test equipment, virtual test equipment that you can use to look at things. And what we're going to want to look at is we're going to want to look at the most importantly, the time and frequency plot. So if you've heard of waterfall plots where you have time and frequency shown together so you can see changes in the signal over time. We're also just going to want to look at the frequency plot so that we can just see for fine details like what's changing. And then we're going to finally want to look at what the time waveform looks at so that we can see fine details in time to better see what's changing, which we may miss in the waterfall plot. And so what we want to then do here is we're going to edit each of the properties. Now I'm going to make the properties for the waterfall, I'm going to make the FFT size a little larger so that it has a little finer resolution for the display. I'm also going to change this to floating point because we're not dealing with complex signals. And then I'm going to change the sample rate to FS and just look through here and going to leave everything else the same. So we do the same thing to the frequency plot. Change. I'm going to leave that just as the 1024. We change the sample rate, and then we go through here, and I'm going to just change the minimum value of the frequency plot to 100 dB instead of 140, just so I get a little more dynamic, a little less dynamic range for the display. And going to, for now, just leave everything else the same. Oh, actually, I forgot to change complex to floating point. Okay, so we're going to do the same thing here with the time sync. And then I'm going to show less samples because this is to visualize, and really about 256 samples is sufficient to be able to see what the signal change. And if you have a lot of samples here, it's going to be hard to see the waveform based on our frequency that we're using. And then just going to leave everything else here, make sure that it actually changed this to floating point, click OK. Now they're still all red because we haven't hooked everything together. We haven't put the outputs to in. Before we do that, we're going to want to use something called a throttle block. That can be found under miscellaneous and throttle. And what this does is for simulations, which this is currently, we don't have it hooked to any real hardware, that for real-time simulations, we want this to run at 44,000 times a second. But if we don't have a throttle block, the GNU Radio will run it as fast as possible. So we want to say that really we want to slow this down to 44,000 times a second because otherwise we'll use up all the CPU resources, and the purpose of this simulation is just to show what it would look like in real time. And I'll make a video. There's some interesting properties when using the throttle block, and so I'll make a video on using that. So now what we're going to do is just connect them together by clicking on the ports, so for the output and input. And as you see, as we do this, it turns from red to black. So everything is now hooked up. This doesn't mean that it's free from errors. It just means that it's all hooked up. So we can run it, and what's going to happen here is that this is going to get compiled into Python code and then executed. And we should be able to see, when we run this, we can see that we've got our waterfall plot where we have frequency and then time, and then our time waveform and our frequency. And so when we go to, and I can change the frequency, it can increase the frequency on the slider, and you can see it move out. You can see this move out. But this really isn't acceptable because and then the amplitude, we can increase the amplitude, and you get to see the effects of when you're sampling. So if we increase and decrease at different frequencies, we can see the effects of sampling when the number of samples per waveform is decreased, because when you go back to here, you can see how it would look more textbook-like. One of the issues, though, with this display is that this isn't very large, and plus these controls are like a little too long. It'd be nice to have it more compact to make it more usable. And then also I'd like the frequency plot to be under here. So what we want to be able to do is tell GNU Radio how to lay that out. And this is done with something called GUI hints. The way to use them is to first decide how we want the GUI to be laid out. So for example, I want the GUI to look like this, where the waterfall plot is at top because it has the most amount of information of both the time and frequency. And then after that, I want the frequency along the same horizontal axis. And the frequency plot can also give me additional information of subtle variations, which may not appear easily in the waterfall plot. And the same goes for the time, where the time can show, it's easier to see slight changes and fluctuation of amplitude, which may not be obvious in the waterfall plot. And we want both then the frequency control and the amplitude control to be easy to adjust while looking at both the waterfall and frequency and time plots. Now, once we have the layout done, we want to think about how to tell GNU Radio this is laid out in terms of a table. And so the way to do this is to look at the components and think about how could we break this up into a set of rows and columns. And I see naturally this could be broken up into two columns, right? We have a column here, we have a column on this side, and then a column on this side. And then we have a set of rows, and the amount of rows depends on the smallest component, which for row height would be the control. So we basically have about, let's say, one row here, another row, that's two rows. This could be a row, a third row, and then we want this larger. So maybe we'll make this like 3 rows here. So we're talking about 6 rows and 2 columns. And so then we create that table. And the important thing to note for GNU Radio is when we go to tell GNU Radio how we want these components laid out on this table, we need to know that GNU Radio wants things to start at 0, not 1. So when we start indexing our table, we say this is the 0th column and not the first column. And this will be the 1 column, even though it's the 2nd column. So to tell GNU Radio where we would want the waterfall component, we tell GNU Radio in these GUI hints that we want the waterfall to start at row 0, And then we would say to where to start column-wise, which would be column 0. And then we would have tell it the row height. So that's three rows high, 1, 2, 3. And how many columns? 2, 1, 2. So then we would proceed on to the taking this information and creating a list out of it to actually type in the GUI hint. So in the GUI hint, we just put the numbers. We just say 0, 0, 3, and 2. Now we do the same thing for the frequency control. So the frequency control is going to start at row 3, column 0, and it's going to be 1 row high and then 2 columns long. And we can see that right there. Start at 3, row 3, column 0, 1 row high, 2 columns long or wide. And we can do the same with the time plot. And that again starts at row 4, column 1, 2 rows high, 1 column wide. And the controls, this control starts at row 4, column 0, and it's both 1 row high and 1 column wide. The same for the second control, which is starting at 5, 0, and then 1 row high and 1 column wide. We take these numbers and we're going to go back to our GNU Radio flowchart, and we're going to enter in this information into each of the GUI hints for the components. So now we're going to add the GUI hints so that GNU Radio knows how to plot the display. And first, I'll edit the signal source, or not the signal source, but can't change that, but we'll edit the range here. So for the frequency range, and for the frequency range, we had 4 starting at row 4, starting at column 4, and then 1 and 1. Spaces here. And then for the amplitude, it was starting at row 5, column 0, and then a width of height of 1 and a width of 1. I'll fix the commas there. I think I have one too many. And we'll get rid of that. Okay. And then for the waterfall plot, which we wanted to have larger, go to GUI hint, and then for that we wanted starting at the top 0, 0, and then wanted it 3 high and then 2 wide. And for the frequency plot, we wanted that much smaller, or much not as tall, and so we'll have that start below the spectrogram at 3, 0, and 1 and 2. And then finally, for the time plot, we want to have that below the frequency plot and by the controls. So start at 4, 1, and then it will be 2 high and 1 wide. Okay, now we go to run this. So we save it, and we go to run it. And it looks better, but one of the issues is this isn't very, this is too tall in relation to this. And the reason why, and also there's sort of dead space here. We only have one, the signal names we really don't care about since we only have one signal. So this is kind of dead space too. So one of the things that we can do is we can actually make the spectrogram have a larger range, is that we can adjust this. And what you actually have to do is you have to go to the config and you turn off the legend, and then for the frequency, we can turn off the axis labels. And then for the time sync, we can either, if we go to config, we can turn off the legend because we don't need that. We can leave the axis label on if we like, and then compare the two. So if you look now with the axis labels turned off, the frequency now takes up much less space. And we can, as an experiment, if we want to turn off the axis labels to see if how much more space we get for the spectrogram, go ahead and just turn those off. Rerun it, and it's actually about the same. So we could turn that back on and just have less area. So this is a trade-off that you have to make for how much area you want versus how much information for the axis labels. And we can see that now with our controls, it's more compact and it's easier to adjust. So what have we learned? Well, we've learned how to implement a sine wave generator using GNU Radio. Additionally, we learned how to customize the display in GNU Radio and some of the finer details of GUI hints and labeling. Now we have something that we can generate sine waves with, and we're going to use this in the remaining videos in the series.